Hello and welcome. Please settle in, close your eyes, and prepare to begin our journey. We all know that iconic phrase from cinema, "In space, no one can hear you scream." It has become the symbol of the absolute, bone-chilling silence of the void. And from a purely physical standpoint, that is true. Sound, as we know it, is a vibration traveling through a medium, like air or water. In a vacuum, it simply has no way to propagate. But what if I told you that wasn't the whole story? What if the universe is actually humming with music, simply played on instruments invisible to the eye and producing sounds undetectable to the human ear? Space is not silent. It whispers, it hums, it sings, and it thunders. In this sleep lecture, we are going to learn how to listen. We will journey through the stars to hear their secret symphony, hidden within radio waves, X-rays, and even the very fabric of space-time itself. Prepare to discover why space is truly whispering sounds no one can hear. Before we venture deeper into the cosmos, let us pause for a moment and understand exactly why we cannot hear it directly. Imagine a bell. When you strike it, it vibrates. Those vibrations cause the air molecules around it to vibrate as well, compressing and expanding. This wave of compression and rarefaction travels through the air, and upon reaching our ears, it causes the eardrum to vibrate. The brain interprets these vibrations as sound. The key word here is air. Sound needs a medium to travel. It can pass through gas, liquid, or solid material. But space is almost a perfect vacuum. Out there, between the stars and galaxies, matter particles are so sparse that a sound wave simply cannot transfer from one to the next. The distance between them can be meters or even kilometers. That's why the space battles in movies, full of booming explosions and rattling gunfire, are purely beautiful fiction. In reality, they would be met with absolute silence. But the universe has found another way to communicate. Instead of sound waves, it uses electromagnetic waves, light, radio waves, infrared, and X-rays. These require no medium and can travel through the vacuum for billions of years. And these waves carry information about the most distant and mysterious objects. Scientists have learned to intercept these signals using vast radio telescopes and convert them into audible sound. This process is called sonification. We don't hear space directly. Instead, we listen to its translation into a language of sound we can understand. And this translation reveals a completely new universe, one that is invisible, yet perfectly audible. All right, let's kick off our journey with the cosmic sounds closest to home, those actually being generated right here in the immediate neighborhood of our own planet. Picture this. Beyond our atmosphere, Earth is shrouded in an invisible protective field. We call it the magnetosphere. This giant magnetic bubble acts as a shield, protecting us from the punishing torrent of charged particles streaming off the sun, what we know as the solar wind. When this solar wind slams into the magnetosphere, it doesn't just flow past. It forces the field to vibrate, sing, and crackle, much like the strings of a giant cosmic harp. Now, these aren't acoustic sounds, they are electromagnetic waves, but satellites equipped with specialized instruments can easily record them. Scientists have named these phenomena chorus waves, or the cosmic choir. If we translate these recordings into the audible range, what we hear is something akin to the chirping of an entire flock of unearthly birds, mixed with whistles and mysterious, ethereal howls. It sounds like a lost soundtrack from a classic sci-fi movie, but it is the authentic voice of our world interacting with the cosmos. These waves are so powerful that they sometimes precipitate particles from Earth's radiation belts down into the atmosphere, triggering the brilliant display of the northern lights. So the next time you look up and see those shimmering green and violet ribbons of the aurora, know that you aren't just witnessing a light show. You are, in a sense, getting a glimpse of the sound behind that majestic cosmic dance. This is the first, and perhaps most intimate sound the cosmos offers us, the protective song of our own planet standing guard against the harsh winds of the universe. It serves as a constant reminder that we are living inside a dynamic, vital system, full of processes that are invisible to the eye, but entirely real. Let's journey a little further out, to the gas giants of our solar system, Jupiter and Saturn. These planets are, in fact, genuine radio signal generators. Their powerful magnetic fields and turbulent atmospheres produce a truly alien cacophony. One of the most famous phenomena recorded by spacecraft like Voyager and Cassini is the so-called whistling atmospherics, or simply whistlers. These signals are born from lightning strikes that can be thousands of times more powerful on Jupiter and Saturn than here on Earth. When a giant bolt of lightning flashes, it generates a radio pulse covering a wide spectrum of frequencies. This pulse travels along the planet's magnetic field lines and disperses within the plasma. Since high-frequency waves move faster than low-frequency waves, they arrive at the spacecraft's receiver first. The result is that when we convert this signal into sound, we hear a characteristic downward-sloping whistle, a sound often compared to a cartoon bomb dropping or a sci-fi laser blast. This fascinating phenomenon allows scientists to study the plasma density around these planets just by listening to the echoes of their massive thunderstorms. Beyond whistlers, the probes record other kinds of sounds. For instance, the Saturnian kilometric radiation, or SKR, consists of intense radio bursts closely tied to Saturn's aurorae. The resulting sonification sounds like a series of eerie, pulsing static, cracks, and clicks, giving the listener the distinct impression of eavesdropping on some kind of alien machinery. Listening to these recordings, we can close our eyes and imagine Jupiter's endless clouds churning with millennia-old storms, or the icy rings of Saturn shimmering under the distant sunlight, all of it set to the soundtrack of their own, unique radio symphony. Now let's step outside the bounds of our own solar system and turn our attention and our ears toward the stars. Stars might appear to be eternal, unchanging pinpricks of light in the night sky, but in reality they are gigantic, turbulent balls of scorching plasma churning with violent processes. These processes, too, generate sounds, or more accurately, vibrations that we can actually listen to. The field dedicated to this study is called astroseismology. Just as geologists use seismic waves from earthquakes to probe the Earth's interior, astronomers analyze these stellar oscillations to map out a star's internal structure. These vibrations cause the star's surface to pulsate ever so slowly and minutely, expanding and then contracting again. These shifts in brightness are far too subtle to be seen by the naked eye. However, sensitive telescopes like the Kepler Space Observatory are able to register them. When scientists analyze this oscillation data and accelerate it millions of times to shift it into the audible range, the result is an astonishing sound, a deep, resonating hum. Every star sings its own unique song. Younger, larger, and hotter stars have a higher pitch, while older, cooler giants like red giants produce a sound that is low and incredibly bass-heavy. Our own sun also vibrates, creating a complex chord made up of millions of different oscillations, though its fundamental tone is far too low, resting deep below the limits of human hearing. By listening to these stellar songs, astronomers can determine a star's mass, its age, its chemical composition, and even what is happening deep within its core. It's essentially like performing an ultrasound scan on a star from trillions of miles away. This deep, enveloping hum of the stars is not just a beautiful effect, it is the authentic voice of their hidden inner life, a profound symphony of thermonuclear reactions and convective flows, reaching us across the vast chasm of time and space. Among the countless stellar voices, there are truly unique performers, a type of cosmic drummer. They are known as pulsars. To grasp their nature, picture a star far more massive than our own sun. When it reaches the end of its life, it explodes as a supernova. Its core then collapses under its own gravity, squeezing down to an unimaginable density. A piece of this matter, the size of a city, would weigh more than all of humanity combined. That is how a neutron star is born. During this collapse, the star dramatically speeds up its rotation, much like a figure skater pulling their arms inward, sometimes spinning hundreds of times per second. This ultra-dense neutron star possesses an extremely powerful magnetic field that channels two narrow beams of radio energy from its poles. These beams sweep across the cosmos like the light of a cosmic lighthouse, rotating along with the star. If Earth happens to cross the path of one of these beams, our radio telescopes register a strictly periodic pulse. That recurring effect is precisely what we call a pulsar. When astrophysicist Jocelyn Bell Burnell first detected this signal in 1967, its uncanny regularity was so striking that it was jokingly dubbed LGM-1, short for Little Green Men 1. Scientists actually considered whether the signal could have an artificial intelligent origin. However, it wasn't long before other pulsars were discovered, confirming that this was a natural phenomenon. When these radio signals are processed through sonification, they translate into a clear, rhythmic ticking, much like a cosmic metronome. Every single pulsar has its own unique tempo, though it slows down infinitesimally over vast stretches of time. This inherent precision allows scientists to use pulsars as cosmic clocks for rigorous testing of general relativity and for the precise detection of gravitational waves. When we listen to this relentless cosmic beat, we are hearing more than just a sound. We are hearing the ticking of the most precise clocks in the universe, remnants of the most magnificent stellar catastrophes. The universe, beyond ordinary stars and exotic pulsars, is filled with truly immense and terrifying objects. Perhaps the most mysterious among them are black holes. These regions of space possess such monstrous gravity that not even light can escape. For a long time, they were synonymous with absolute void and silence. However, in 2003, astronomers using the Chandra X-ray Observatory made an astonishing discovery that completely changed our understanding. They were observing a giant cluster of galaxies in the constellation Perseus, about 250 million light-years away. At the heart of this cluster sits a supermassive black hole. The astronomers noticed that the hot gas filling the cluster exhibited concentric waves, much like ripples on a pond after dropping a stone. These waves turned out to be sound waves. The source was the black hole itself, periodically emitting powerful jets, streams of high-energy particles that agitate the surrounding gas and create this gigantic sonic ripple. Scientists were able to calculate the frequency of these oscillations. They corresponded to the note B-flat, but an astonishing 57 octaves lower than middle C on a piano. One full oscillation of this wave takes nearly 10 million years to complete. This is the lowest note ever detected in the universe. Our ears, of course, cannot perceive such infrasonic vibrations. But in order for us to hear it, NASA scientists had to increase the signal frequency by tens of octaves. The result was a deep, eerie, otherworldly hum. This isn't just an artistic interpretation, this is the real sound propagating right now through the gas of the Perseus galaxy cluster. We are listening to the hum of a supermassive black hole, the low, rumbling voice of one of the most powerful objects in the cosmos. Black holes don't just make sound through the gas surrounding them, they can generate acoustic information in a far more fundamental way through the ripples and vibrations of space-time itself. According to Einstein's general theory of relativity, massive objects curve the space-time around them. When incredibly dense objects like two black holes or two neutron stars orbit each other and finally merge, they create a disturbance, a ripple in space-time that travels outward in all directions at the speed of light. These are known as gravitational waves. For a long time, these waves were nothing more than a theoretical prediction. But in 2015, the LIGO Observatory achieved a historic first, directly detecting such a wave from the merger of two black holes that occurred over 1 billion years ago. LIGO's detectors are unbelievably sensitive instruments capable of measuring a change in distance thousands of times smaller than the diameter of a proton. When a gravitational wave passes through Earth, it momentarily compresses and stretches everything in its path, including the arms of the detector itself. The subtle vibration signal recorded by LIGO can then be converted into an audible sound wave. What we hear is a short, rapidly rising tone, often described as a chirp or a quick click. Scientists universally refer to this signature sound as the chirp. This sound lasts for only a fraction of a second, yet it contains the signature of a monumental cosmic catastrophe. By listening to this chirp, we hear the final deadly crescendo of two black holes completing their orbital dance. We can determine their masses, their rate of spin, and exactly how much energy was radiated away as gravitational waves. In a mere fraction of a second, these events release more energy than all the stars in the universe emit combined. This is more than just a sound, it is the very vibration of the cosmos reaching us across the abyss of time. We've listened to planets, stars, and black holes, but what about the biggest thing we can possibly imagine? What about the sound of the universe itself being born? Of course, there was no air during the Big Bang to carry sound waves, yet the early universe wasn't an empty vacuum. For the first few 100,000 years after its inception, it was filled with a superheated, incredibly dense plasma, a kind of primordial soup made of protons, electrons, and photons. This plasma was so dense that light couldn't travel freely. It was constantly scattered by particles. Within this soup, monumental processes were taking place. Dark matter used its gravity to try and compress the regular matter, while the tremendous pressure of the hot photons fiercely resisted this collapse. This powerful conflict generated gigantic pressure waves that rippled throughout the young universe. These were genuine sound waves, but their medium was this primordial plasma. These waves, known as baryon acoustic oscillations, were unimaginably powerful and enormous. Some spanned hundreds of thousands of light-years in length. Then, approximately 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to finally combine into stable hydrogen atoms. At this exact moment, the universe became transparent to light. The photons that had previously been trapped within the plasma finally broke free and shot out in every direction. We can still observe this first light today in the form of the cosmic microwave background radiation, or CMB. And on the map of this radiation, like imprints left on ancient parchment, the traces of those very sound waves were left behind. By analyzing these tiny temperature fluctuations, scientists have been able to reconstruct the sound of the early universe. If you compress those 380,000 years down into just a few seconds and raise the frequency, you would hear a growing, deafening roar that cuts off abruptly the moment the light is liberated. This is the voice of the infant universe, the roar of its birth, frozen in eternity. Let's step back from the grand scale and focus on something more immediate and perhaps easier to grasp. How can we be sure that all these cosmic sounds we're discussing aren't just scientific conjecture or random noise? This is where mathematics and computational modeling come into play. Sonification is not about arbitrarily slapping sound onto data. It is a rigorous scientific method that aims to convey the characteristics of the source signal with the utmost accuracy. Imagine you have a graph tracking a star's brightness over time. The luminosity fluctuates, creating a complex, intricate curve. To turn this into sound, we map the time axis of the graph to the timeline of the audio file, and the brightness axis to either volume or pitch. In this way, a peak in brightness translates to a loud or high-pitched sound, while a dip corresponds to a quiet or low tone. The result is an audio track that precisely mirrors every nuance of the original data set. This allows the human ear, which is evolutionarily excellent at recognizing patterns and anomalies, to analyze scientific data in a completely novel way. For example, a faint, periodic signal from a new pulsar might be hidden within a torrent of radio telescope data. Visually, that blip might be nearly indistinguishable from the background noise on a chart. But once this data is sonified, our sense of hearing can instantly pluck that repeating rhythm out of the chaos. Many genuine discoveries have been made exactly this way, by ear. Scientists aren't using sonification just to popularize their work, however. It's a powerful tool for serious analysis. They can listen to solar wind data to predict geomagnetic storms or analyze the sound of gravitational waves to decipher the properties of black holes. So, the next time you hear the voice of the cosmos, remember this. Behind the poetry lies rigorous science, transforming invisible data into meaningful, informative sound. We've already talked about the radio waves that reach us from various cosmic objects, but where exactly do they originate, and how do we actually detect them? To understand this, let's imagine a standard radio receiver. When you tune it to a specific station, you are catching the radio waves broadcast by that station's transmitter. The universe is filled with similar natural radio stations. These can be rotating planets, exploding stars, active galactic nuclei, and even cold gas clouds located between the stars. They emit radio waves for various reasons, stemming from the movement of charged particles in magnetic fields, thermal radiation, or specific quantum transitions within atoms. To capture these incredibly weak signals, which have often traveled thousands or millions of years to reach us, we need giant ears, radio telescopes. Unlike optical telescopes, which collect visible light, radio telescopes are massive parabolic antennas. They resemble satellite dishes, but on a much, much larger scale. The largest of these can span hundreds of meters in diameter. Their primary task is to focus the incoming radio waves to a single focal point, where a sensitive receiver is placed. This receiver then amplifies the signal and converts it into digital data that can be analyzed by computers. Sometimes a single telescope isn't enough. To obtain a much sharper image or a clearer sound, astronomers use a technique called interferometry. This involves combining signals from several radio telescopes located great distances apart. Together they work as one gigantic virtual telescope, the size of a continent, or even the entire planet, such as in the Event Horizon Telescope project, which successfully captured the first ever image of a black hole. It is precisely thanks to these technologies that we can successfully tune in to the right frequency and listen to the whisper of a pulsar, the hum of a galaxy, or the echo of the Big Bang, isolating these specific transmissions from the general cosmic noise. Now that we've covered the tools, let's pivot back to the sources of sound. This time, we're diving into the most violent and chaotic regions of the cosmos, supernova remnants. When a massive star burns through its fuel, it undergoes a catastrophic collapse followed by an explosion of unbelievable power. This supernova blast can briefly outshine the entire host galaxy. The resulting explosion blasts the star's material into surrounding space at speeds reaching tens of thousands of kilometers per second. This expanding cloud of gas and dust, illuminated from within and superheated by powerful shock waves, is what we call a supernova remnant. Perhaps the most famous example is the Crab Nebula, the debris field left behind by a stellar explosion that was famously recorded by Chinese astronomers in the year 1054. At the heart of this nebula sits a rapidly spinning pulsar, the cosmic drummer we've mentioned before. But it's not just the pulsar that produces a signal. The nebula itself is also singing. It is a powerful source of both radio waves and X-rays. This radiation is generated when electrons accelerated to nearly the speed of light by the pulsar's intense magnetic field spiral through space. This process is known as synchrotron radiation. If we point a radio telescope at the Crab Nebula and convert the resulting data into sound, a process called sonification, we won't pick up the crisp beat of the pulsar. Instead, what we hear is a powerful, persistent, hissing static, much like an untuned radio receiver. This noise is literally the sound of chaos, the voice of unbelievable energy unleashed during the star's demise. By analyzing different regions of the nebula across various frequencies, scientists can map its structure, determine the gas temperature and density, and understand how the powerful shockwave interacts with the surrounding interstellar medium. This pervasive hiss isn't merely static or interference, it is an informational hum. It tells the complete story of the giant star's final moments, detailing how its scattered remains enrich the galaxy with the heavy elements necessary for the eventual formation of new stars and planets. Beyond the screams of dying stars and the steady rhythm of pulsars, space holds a much quieter, yet equally crucial, whisper. This is the voice of the cold interstellar gas from which new stars are born. You might think the vast expanse between stars is an absolute void, but that's far from true. It is actually filled with highly diffuse gas, mostly hydrogen, and microscopic dust particles. In certain regions, this gas condenses into gigantic molecular clouds. These clouds are incredibly cold, their temperature hovering just a few dozen degrees above absolute zero. Under these conditions, hydrogen atoms exist in their fundamental, unexcited state, and it is right here, in this frigid environment, that one of the most important phenomena for radio astronomy takes place. A hydrogen atom is simply a proton and an electron. Each of these particles has its own rotation, or spin. These spins can either align in the same direction, parallel, or face opposite directions, anti-parallel. The parallel spin state holds slightly higher energy. Every few million years, the electron spin in a hydrogen atom spontaneously flips, dropping into the more stable anti-parallel state. When this happens, a minuscule packet of energy is released in the form of a radio wave, specifically one with a wavelength of 21 centimeters. That may sound negligible, but giant interstellar clouds contain an unimaginable number of hydrogen atoms. Collectively, all these atoms generate a faint, yet perfectly detectable, radio emission at this fixed frequency. By tuning a radio telescope to the 21 centimeter wavelength, we can effectively hear these clouds. Their signal, when sonified, sounds like a soft, steady hiss. By analyzing the Doppler effect, the shift in the frequency of this signal, astronomers can determine how fast the cloud is moving, either toward us or away from us. This technology allowed us to map the spiral arms of our own galaxy, the Milky Way, for the very first time. We were able to visualize the structure of our stellar home while standing inside it, simply by listening to the quiet whisper of cold hydrogen drifting through the cosmic void. Let's turn our attention back to the Sun, our daytime star. While it seems like a gentle, constant source of light and warmth, the reality is that it is a dynamic and sometimes incredibly violent object. On its surface, flares and coronal mass ejections, gigantic eruptions of plasma and magnetic fields, are constantly happening. These events generate powerful streams of charged particles and intense bursts of radio emission that travel all the way to Earth, potentially triggering geomagnetic storms. Radio telescopes, specifically tuned to solar activity, detect these bursts. Through the process of sonification, these signals are transformed into a wide variety of sounds. Some sound like sharp crackles, others like the distinct wail of a siren, and still others like rapid chirping. These sounds, known as solar radio bursts, are classified by type. For instance, type 3 bursts, which are linked to electron streams, produce a fast, frequency-drifting whistle when sonified. Conversely, type 2 bursts, caused by shock waves moving through the solar corona, manifest as a low hum that slowly descends in pitch. By listening to the Sun in the radio spectrum, scientists can track its activity in real time. This is far more than just scientific curiosity. Powerful solar flares have the potential to disrupt satellites, navigation systems, and even electrical grids here on Earth. Therefore, continuous radio monitoring of the Sun is a crucial component of the space weather system, helping us predict and mitigate the consequences of solar storms. So, this crackle and howl we hear from the depths of space isn't merely an abstract sound. It is the voice of our closest and most powerful neighbor, directly influencing our lives and the technology we rely on. It serves as a potent reminder that we live in an active and ever-changing environment, and that even our home star possesses its own unique and rather formidable voice. Up until now, we've focused on cosmic sounds that are either steady, like the deep hum of a black hole, or predictably periodic, like the rhythmic beat of a pulsar. But the universe has a serious knack for throwing curveballs. In 2007, astronomers discovered a completely new and utterly baffling type of signal. It was a tremendously powerful radio burst, lasting just a few milliseconds. Yet in that fleeting moment, it unleashed the equivalent energy our Sun produces over several days. The signal originated in a distant galaxy and its nature was totally incomprehensible. This phenomenon was named a fast radio burst, or FRB. Since then, hundreds of these bursts have been detected. Some were one-offs, flashing just once before falling silent forever. Others, much to scientists' astonishment, proved to be repeaters emitting series of pulses. The sonification of these signals produces a very distinct sound, a short, sharp whip crack or an electronic pew. When a burst repeats, we hear a series of these clicks, sometimes following one another at chaotic, unpredictable intervals. The origin of fast radio bursts remains one of the central mysteries of modern astrophysics. There are numerous hypotheses. Some scientists believe the source could be magnetars, a special type of neutron star with extremely powerful magnetic fields. Others speculate they might be caused by the merger of compact objects, or perhaps something even more exotic entirely. As we listen to these mysterious clicks echoing from intergalactic space, we are essentially bearing witness to the solving of one of the universe's greatest puzzles. Every new burst detected, every new piece of sonified data brings us closer to understanding what kind of cataclysm, what event of monstrous power can generate such a brief and mighty cry, audible across half the cosmos. We've spent a lot of time discussing the sounds made by individual cosmic objects, but what if we tried to listen to an entire galaxy? Our own galaxy, the Milky Way, is a colossal system, home to hundreds of billions of stars, gas, dust, and dark matter. While it doesn't produce a single, distinct sound, if we point a radio telescope toward its center or along its plane, we pick up a complex blend of signals coming from countless different sources. This collective background hum of galactic radio emission, this is what we call the voice of the Milky Way. So what would we actually hear if we took that signal and turned it into sound? It wouldn't be a melody or a clear, rhythmic beat. Instead, it would be a deep, complex, and constantly shifting noise. Within this noise, you could distinguish the hissing sound of synchrotron radiation emitted by electrons speeding through the galaxy's magnetic fields. You might also detect a quieter background coming from distant supernova remnants and active star-forming regions. If you aimed the telescope precisely at the galactic center toward the constellation Sagittarius, that noise would grow louder and more intense. There, at the very heart of the Milky Way, lurks the supermassive black hole Sagittarius A9. It isn't as intensely active as the black hole in the Perseus Cluster, but it is still surrounded by hot gas that strongly emits radio waves. This powerful central hum acts like the very heartbeat of our galaxy. By listening to this galactic noise, we can truly begin to grasp the sheer scale and complexity of our cosmic home. It's much like standing blindfolded in the middle of a massive city and simply listening. You can't make out individual conversations, but the city's general rumble gives you an undeniable sense of its life, its energy, and its size. Similarly, by listening to the Milky Way's radio noise, we feel its grandeur and respiration. We hear the collective voice of billions of stars and nebulae. Billions of other galaxies lie beyond our own, and in a way they make noise too. Galaxies that are actively forming new stars, known as starburst galaxies, are powerful sources of radio emission. Within their giant molecular clouds, thousands of massive stars are born. These stars live fast and die young, exploding as supernovae. This process floods the galaxy with cosmic rays, creating a powerful radio hiss, or static. But there is another, even louder, type of galaxy. These are called active galaxies, or quasars. At their centers reside supermassive black holes that are actively devouring their surroundings, gas, dust, and even entire stars. As this matter falls inward, it spirals into what is known as an accretion disk. Friction within this disk heats the material up to millions of degrees, causing it to glow fiercely across the entire electromagnetic spectrum, including radio waves. Often, two gigantic jets of plasma, known simply as jets, erupt from the center of this system. These jets can stretch for millions of light years, extending far beyond the galaxy itself. These are some of the most powerful radio sources in the universe. If we sonify the radio signal from a distant quasar, what we hear is a powerful, steady roar. It is the sound of matter being shredded and consumed by a gravitational monster. This roar represents an outflow of energy equivalent to hundreds of normal galaxies, yet it is erupting from a region no larger than our own solar system. By listening to these distant voices, we are looking back into the universe's past, because the light and radio waves have taken billions of years to reach us. We hear what the universe sounded like in its turbulent youth, when galaxies were more active and their central black holes were truly insatiable predators. This roar is the soundtrack to an age of cosmic titans. Beyond discrete individual objects, there is a pervasive background noise that permeates the entire cosmos. We've already discussed the cosmic microwave background, the microwave echo of the Big Bang, but there is also the cosmic radio background, which is the cumulative radiation from every radio source in the universe, sources too distant or too faint to be distinguished individually. Imagine being in a huge stadium during a game. You hear the collective roar of the crowd, the shouts, the conversations, the applause of thousands, yet you can't make out a single individual voice. The cosmic radio background is exactly like this. It's the crowd noise generated by billions of distant galaxies and quasars. If you were to convert this signal into sound or sonification, it would simply register as a hiss, much like standard white noise. Yet for cosmologists, this noise holds invaluable information. By studying its intensity and distribution across the sky, scientists can draw conclusions about how the first stars and galaxies formed and how the epoch of reionization unfolded, that period when the light from those initial stars burned through the neutral hydrogen fog that filled the young universe. This noise acts like an archaeological layer, concealing data about the earlier stages of cosmic structure evolution. Scientists are now attempting to subtract the signals from all known nearby sources from this general background in order to isolate the faint, ancient emission originating from those very first stars. This is an incredibly difficult task, akin to trying to hear a whisper across the stadium just as the winning goal is scored. But if they succeed, we will finally be able to hear the cosmic dawn, the moment when the first lights ignited in the universe, ending the long, dark ages. Let's discuss exactly how sonification aids discovery. A prime example is the well-known story of the first pulsars detection. Graduate student Jocelyn Bell Burnell was sifting through kilometers of paper charts from radio telescope recordings. She spotted a strange, repetitive signal, a tiny blip on the chart, recurring precisely every 1.33 seconds. At first, this was dismissed as mere noise or interference, but if she had been able to listen to that data, her ear would have instantly picked out that clear, metronomic rhythm from the background static. Human hearing possesses a unique and powerful ability to recognize temporal patterns. We can differentiate random noise from music, speech from a shout, or the drumming of rain from approaching footsteps. Scientists are now actively leveraging this innate ability. In the gravitational wave search project LIGO, data isn't analyzed only by computers. There is also a citizen science project called Gravity Spy, where volunteers can view and listen to sonified glitches, brief bursts of noise within the detectors. By classifying these sounds, people help train artificial intelligence to better distinguish a true astrophysical signal from detector artifacts. Another example is asteroseismology. By analyzing the song of a star, we can hear not just its fundamental tone, but also its overtones, beats, and changes in timbre. These subtle nuances, which might be difficult to spot on a visual graph, sound to a trained ear like distinct shifts in harmony. They can reveal the presence of orbiting planets, internal core processes, or confirm the star is part of a binary system. Sonification transforms abstract datasets into something immediately intuitive, allowing scientists to leverage one of the most sophisticated pattern recognition tools nature has given us, our sense of hearing. It's important to understand that sonification isn't purely science. It's also, to a significant degree, an art form. There is no single, universally correct way to translate data into sound. The scientist or artist engaging in sonification must make several creative choices, For instance, which data attribute do we map to pitch and which one to loudness? Should we perhaps use different musical instruments entirely for different signal types? For example, a pulsar signal might be rendered as a sharp drum beat, while the subtle fluctuations of a magnetosphere could be represented by the smooth sound of a flute or a synthesizer. These mapping decisions fundamentally influence our perception. A black hole's sound, when presented as a low, ominous rumble, evokes a certain set of emotions. If the exact same data were rendered as a high, clear tone, our entire impression would shift dramatically. This element of subjectivity doesn't make the method any less scientific, provided the fundamental data patterns are accurately preserved. In fact, this artistic leeway opens up powerful new avenues for communication. Artists and musicians, such as Matt Russo or those behind the System Sounds project, create entire musical compositions based on astronomical data. For instance, they might take the orbital data of the planets in the TRAPPIST-1 system and assign a unique note to each planet. The result is a unique, harmonious melody generated by their movement as they orbit their star. These projects help audiences far removed from academia truly feel the beauty and harmony of the cosmos. They translate complex scientific concepts into the universal language of music, evoking wonder and giving us a profound sense of connection to these great discoveries. It acts as a bridge between the world of rigid formulas and the realm of human emotion, demonstrating that the universe is not only knowable, but profoundly beautiful. While we talk about the sounds of space, it's vital to grasp the true scale involved. The processes we listen to unfold across vastly different timescales than those we experience daily. We've mentioned before that a single oscillation of a sound wave from the black hole in the Perseus Cluster lasts 10 million years. To make that audible, we have to compress those 10 million years into a single second. Even the pulsations of an ordinary star, like our own sun, have periods lasting several minutes. To transform them into an audible hum, we must speed up the recording thousands of times over. The rotation of planets, which forms the melody in projects like System Sounds, actually takes days, months, and years. We accelerate time simply to catch the music. On the flip side, we deal with ultra-fast processes. A fast radio burst, or FRB, lasts mere milliseconds. To analyze and even perceive this event, scientists must do the opposite. They slow down time, stretching out that incredibly brief impulse. This dynamic manipulation of timescales is one of the most astonishing features of sonification. It allows us to perceive the rhythms of the universe that are completely inaccessible to our direct, lived experience. We can hear the slow, million-year-long breath of a galaxy and the ultra-short scream of a dying star that happens in an instant. This grants us a truly unique sense of perspective. Our own lives, the entire history of humanity, are just a brief flicker compared to these immense cosmic cycles. By listening to the accelerated song of a star or the slowed-down pulse from the intergalactic void, we momentarily step outside our conventional human perception of time. We touch eternity, the fundamental, enduring rhythms of the universe itself. Let's come back down to Earth and talk about what these cosmic sounds actually look like, or more accurately, how sound waves can help us see the universe. We're talking about data visualization, a process that often goes hand in hand with sonification. Think of a sound spectrogram. It's a graph that illustrates how the frequency composition of sound shifts over time. It clearly shows the high and low notes, their duration, and their volume. Similar visualization techniques are applied directly to cosmic signals. For example, a pulsar signal, when mapped on a spectrogram, appears as a series of vertical lines repeating at fixed, regular intervals. The characteristic chirp from a black hole merger, however, shows up as a smoothly curving line moving from the bottom to the top, signifying a rapid increase in frequency. These visual patterns are just as rich in information as the sound data itself. Sometimes, astronomers go further, creating more complex three-dimensional visualizations. Imagine a simulation detailing the merger of two neutron stars. The computer calculates the changes in density, temperature, and the gravitational field at every single moment. This resulting data can then be both sonified and visualized simultaneously. For example, the loudness of the sound might correspond to the intensity of the gravitational waves, while the color in the image represents the temperature of the matter. The result is not merely a video, but a complete, immersive audiovisual experience that allows us to both see and hear the reality of a cosmic catastrophe. These simulations help scientists better grasp the physics of extreme events, allowing them to compare their theoretical models against real-world observations. For us, the viewers, it's an incredible opportunity to peer into the very heart of processes that are impossible to observe directly, feeling their power and beauty through this synthesis of sound and imagery. Ultimately, this is another powerful method of translating the language of the cosmos into a human language, the language of the senses. We already know space is saturated with radio waves, but does true acoustic sound actually exist out there? The surprising answer is yes, but only in extremely specific, localized environments. Sound requires a medium, and while the space between stars is a vacuum, certain cosmic objects do provide that environment. Take stars, for instance. A star isn't a solid ball, it's a colossal sphere of extremely hot and dense plasma. Inside, continuous convection processes take place. Hot plasma rises from the core to the surface, cools, and then sinks back down. These turbulent flows generate sound waves that travel throughout the star. These very waves cause the vibrations that the field of astroseismology studies. So deep within stars, there truly is a continuous, deafening roar. Another example can be found in gaseous nebulae, especially young star-forming regions. While the gas density there is negligible by Earth standards, it's still not zero. When a massive hot star is born nearby, its powerful radiation and stellar wind begin to intensely push on the surrounding gas, compressing it and creating shock waves. These shock waves, which are essentially extremely slow, long acoustic waves, travel through the nebula, condensing the gas and triggering the formation of new stars. We cannot hear this sound directly because its wavelength can span light years, and its frequency might be only one oscillation every few thousand years, but they are real pressure waves propagating through the interstellar medium. And finally, of course, planetary atmospheres. In the atmospheres of Jupiter or Saturn, hurricanes rage with wind speeds reaching hundreds of kilometers per hour, illuminated by colossal lightning strikes. If we could lower a microphone into that environment, we would hear a continuous roar of wind and deafening cracks of thunder. So, space is not entirely silent. In its distinct corners, in the hearts of stars and the clouds of nebulae, its own acoustic symphonies play out, inaccessible to us directly, yet undeniably real. Beyond the natural sounds of the cosmos, space is increasingly being filled with those of artificial origin. Since the very dawn of the space age, humanity has been sending radio signals into the void. The earliest satellites, including the famous Soviet Sputnik 1, transmitted simple signals back to Earth, signals easily picked up by any amateur radio operator. Its iconic beep, beep, beep became the first artificial voice heard in space. Since then, we have launched countless signals. These include command codes for controlling spacecraft, the telemetry they beam back, scientific data from Mars rovers, and the signals that power the GPS system. All this activity collectively creates a constantly shifting sphere of artificial radio emission surrounding Earth. But what about messages intended for extraterrestrial civilizations? The most famous example is the Arecibo message, beamed out in 1974 toward the M13 globular cluster. It is a coded radio transmission containing basic information about humanity. If you were to sonify it, it would sound like a short series of varying musical tones. A far more poetic example involves the golden records aboard the Voyager 1 and Voyager 2 probes. Alongside images and greetings in different languages, these records carry sounds, the rustling of wind and rain, birdsong, and music ranging from Bach to Chuck Berry. This is not a radio transmission, but a physical medium, a cosmic message in a bottle cast into the expanse of space. These probes have already left our solar system and are now traveling through interstellar space, Perhaps tens of thousands of years from now, someone might find them and be able to hear the voices of our planet. In this way, humanity adds its own unique notes to the great symphony of the universe. What does the future of listening to the cosmos hold? It promises to be even more thrilling. New, highly sensitive telescopes are currently being built both on Earth and in space. Take the colossal Square Kilometre Array, or SKA, for instance. This giant radio telescope will utilize thousands of antennas spread across Australia and South Africa. With a combined collecting area of 1 square kilometre, it will officially be the largest telescope ever constructed. It will be able to peer back into the universe's earliest epochs, map hydrogen distribution, discover thousands of new pulsars, and potentially detect the faintest gravitational waves. The sheer volume of data this telescope will generate is expected to exceed the entirety of today's global internet traffic. Manually analyzing this much information will be impossible. This is where artificial intelligence steps in. Machine learning algorithms will wade through these petabytes of data, searching for familiar sound patterns and identifying entirely new, unknown types of signals. AI may be capable of finding subtle correlations within the cosmic background noise that the human ear, or eye, could never possibly perceive. Simultaneously, gravitational wave observatories are evolving rapidly. Plans are underway to launch the LISA Space Interferometer, which will consist of 3 satellites forming a gigantic triangle in space with sides measuring 2.5 million kilometers long. LISA will be sensitive to the ultra-low-frequency gravitational waves that cannot be detected from Earth. It will be able to hear the monstrous mergers of supermassive black holes at galactic centers, binary systems of white dwarfs, and potentially even the gravitational ripples born in the very first moments after the Big Bang. We stand on the cusp of a groundbreaking new era in astronomy, where we will not only be able to see the universe, but also hear it with unprecedented clarity. Listening to the cosmos also poses profound philosophical questions. When we transform impersonal data, photons, radio waves, gravitational waves, into sound, we are, in effect, humanizing the universe. We utilize hearing, one of our most ancient and emotionally resonant senses, to perceive it. This fundamentally alters our relationship with space. It ceases to be merely a cold, empty void. Instead, it becomes something living, dynamic, and filled with voices. We begin to speak of stars singing, gas whispering, and quasars roaring. These are, of course, metaphors, but they help us forge a closer, more intuitive connection with creation itself. This also raises the question of our place in the universe. Listening to the echo of the Big Bang, we touch the moment of our shared genesis. Listening to the hum of the Crab Nebula, we hear how heavy elements, carbon, oxygen, iron, were forged in the furnace of a supernova. These are the very elements that make up ourselves, our planet, and everything around us. We are literally stardust, and the sounds of the cosmos serve as a constant reminder of that fact. But what if, amidst all this natural noise, we were to hear something else entirely, a signal bearing the hallmarks of artificiality, complexity, and deliberate meaning? The search for extraterrestrial intelligence, the SETI project, is essentially an attempt to distinguish an alien voice within the cosmic chorus. What would we feel in that moment? Wonder? Joy? Fear? Listening to the universe is not just a search for knowledge, it is a search for ourselves, for our origins and our potential future. Let's indulge our imagination for a moment. What else might we be able to listen to if our technology were just a little more advanced? For instance, imagine detecting neutrinos, those tiny, nearly massless particles born from nuclear reactions deep inside stars and during supernovae explosions. They barely interact with matter, zipping right through planets and stars as if they weren't even there. If we could build sensitive enough detectors and sonify the neutrino stream, we could essentially hear what is happening right now in the very core of our sun. It would be the most direct, live report we could ever get from the center of a star. What about dark matter? This mysterious substance makes up about 85% of all matter in the universe, yet we still have no idea what it's truly made of. Some theories suggest that dark matter particles might annihilate one another, producing gamma rays or other detectable particles in the process. If we detected such a signal coming from the galactic center, where dark matter is expected to be highly concentrated, we could sonify it. What would the sound of dark matter actually be? Perhaps a barely audible, high-frequency whisper permeating everything around us. And what about wormholes or other dimensions, assuming they exist? Is there any way they might sound in our universe? Perhaps they create specific distortions in space-time that could be picked up as a unique gravitational wave signature. These are currently just theories, but they illustrate just how much uncharted and unheard territory the cosmos holds. Every new ear we turn toward the sky, be it a radio telescope, a gravitational wave detector, or a neutrino observatory, has the potential to unlock a completely new sonic palette of the universe. But beyond pure science, cosmic sounds are increasingly being applied in art and even in therapy. Musicians and composers use this sonified data either as a source of inspiration or sometimes even as the core foundation for their work. An electronic musician might take the steady rhythm of a pulsar and use it as a drum track in their song. An avant-garde composer, on the other hand, could construct an entire symphony based purely on the subtle fluctuations of the cosmic microwave background radiation. This gives rise to an entirely new musical genre, cosmic ambient, where the listener can truly immerse themselves in the atmosphere of distant worlds. Visual artists create stunning installations where the sounds of space control light, color, or the movement of objects, resulting in a unique, multisensory experience. But the applications are even more practical. Calming, monotonous, or slowly shifting sounds like the hum of the stars or the singing of the magnetosphere are now being utilized in sound therapy for relaxation, meditation, and to combat insomnia. This connection is precisely why you might be listening to this lecture right now. The deep, low-frequency sounds of the cosmos can help slow the heart rate and breathing, release tension, and induce a profound state of rest. It acts as a kind of natural white noise, or perhaps more accurately, cosmic noise, that effectively screens out everyday distractions and primes the brain for deep rest. As we listen to these sounds, we intuitively feel something vast, eternal, and profoundly quiet. This helps our own anxieties and daily worries seem less significant when viewed against the sheer scale of the universe. Thus, the voices of distant stars and galaxies, having passed through the filters of science and technology, return to us as a therapeutic lullaby, helping us find peace and harmony. The sheer diversity of cosmic sounds is one of their most striking aspects. The universe, it turns out, isn't playing a single, monotonous tune. Its sonic palette is incredibly rich. We have the clear, mechanical rhythms of pulsars, sounding like precise cosmic clockwork. There is the chaotic, furious hiss of supernova remnants, like the distant echo of an enormous explosion. We detect the deep, vibrating hum of stars, often compared to the resonant chanting of Tibetan monks. There is the eerie, otherworldly howl of black holes. We hear the unearthly chirps and whistles from the magnetosphere of our own planet. Then the short, sharp clicks of mysterious fast radio bursts, and the soft, almost inaudible whisper of cold hydrogen moving through the spiral arms of a galaxy. Dominating all of this is the deafening, yet long silent roar of the Big Bang itself, frozen in the cosmic microwave background radiation. Each of these sounds tells its own story, a story of the birth, life, and death of stars, a narrative detailing the cosmic dance of planets and galaxies, a history built around the most fundamental laws of nature, the physics governing gravity and light. This symphony wasn't composed by any single artist. It arises spontaneously from the complex physical processes unfolding across the farthest reaches of the cosmos, and the fact that we, beings living on a tiny planet orbiting one star among billions, have managed to create the tools and methods necessary to hear this grand music is arguably one of the greatest achievements of the human mind. We learned how to listen to the universe, and in return, it answered us with a chorus of trillions of voices. Perhaps you are wondering, can you actually hear the cosmos yourself without access to giant professional telescopes? The answer, in a way, is yes. Of course, you can't hear radio waves from space directly, but there are several accessible ways to tap into this experience. There are countless online archives on the websites of NASA, the European Space Agency, and various universities, where sonified recordings of all sorts of cosmic phenomena are uploaded. You can find the Earth's own chorus, the rhythmic beat of pulsars, and the low hum of a black hole. Listening to these recordings with a good set of headphones can be a truly meditative experience. Furthermore, there are planetarium programs and mobile apps that don't just show you a map of the night sky, but sometimes incorporate sonified data or thematic soundtracks to help set the right atmosphere. There is also a more direct approach. Radio amateurs with sufficiently sensitive equipment can actually pick up certain cosmic signals. For example, they can catch radio waves bouncing off meteor trails in the atmosphere, or even the faint radio emissions from Jupiter. While this requires specific knowledge and equipment, it certainly proves that the line between professional and amateur astronomy isn't as impenetrable as we might think. But perhaps the most profound way to hear the cosmos is simply to step outside on a clear night, away from the city lights, and look up at the stars. Try to imagine that every single point of light is a colossal, humming ball of plasma, that between them drift invisible clouds of gas, whispering on their own radio frequencies, that somewhere deep out there pulsars are spinning, pounding out their cosmic rhythm. This mental experiment, this connection of imagination to scientific knowledge, is the most accessible way to hear the silent music of the spheres. Let's wrap this up. Why exactly does space whisper? It whispers because it isn't empty. It is saturated with energy, matter, and fields. It whispers through the language of electromagnetic waves, which carry information about the universe's most violent and most tranquil processes. It sings through the vibrations of stars, revealing their internal structures. It pulses with the rhythm of neutron stars, the ultra-dense remnants of stellar catastrophes. It hums with the voices of black holes which stir up the gas in galactic clusters. It screams through gravitational waves, born from the cataclysms of massive object mergers. And it still holds the echoes of its own birth, recorded in the cosmic microwave background radiation. We cannot hear this whisper with our own ears because our senses are adapted to vastly different conditions, specifically the dense atmospheric environment of our planet. But we overcame this limitation using our intellect. We built new ears, radio telescopes, X-ray observatories, and gravitational wave detectors. And we created a new way to listen, sonification, which translates the invisible, inaudible language of the cosmos into understandable sound. This translation allows us not only to gain new scientific data, but also to experience the universe in a new way, to feel its scale, its drama, and its harmony. The cosmic whisper is proof that the universe is not cold and dead. It is alive, breathing, changing, and it possesses its own unique voice. We only need to learn how to listen to it. And now, as you lie here, eyes closed, preparing to drift off, let these cosmic sounds form the perfect backdrop for your deep rest. Imagine not absolute silence, but a space filled with a profound, pervasive hum. This is the underlying ambient noise of the universe itself, the combined voices of billions of distant galaxies creating a deep, resonant drone. Against this vast background, like individual instruments in an orchestra, other distinct sounds occasionally emerge. Hear a rhythmic, crisp tock drift past you. That's a distant pulsar, meticulously keeping cosmic time. Now you catch a smooth, shimmering tone, almost like the song of a distant whale. That's the solar wind playing the magnetic strings of Earth's magnetosphere, creating the brilliant colors of the auroras. Suddenly, a short, sharp, click echoes from another galaxy. This is a mysterious fast radio burst, an event whose nature we still cannot fully explain. And somewhere in the deepest reaches, just at the edge of hearing, a super low note vibrates. This is the song of a supermassive black hole at the center of a distant cluster. All of these sounds blend into one grand symphony. A symphony that has been playing for 13.8 billion years. It has no beginning and no end. It simply is. And right now, in this moment, you are an intrinsic part of it. Your breathing is a rhythm. The beating of your heart is a steady pulse. Allow these cosmic rhythms to gently lull you to sleep. Feel yourself merging with this vast-sounding organism that is the universe. May your sleep be as deep and peaceful as the silent whisper of cold hydrogen gas within the spiral arms of the Milky Way. Good night. So, our journey through the sounds of the universe draws to a close. We've learned that space, contrary to popular belief, is far from silent. It is, in fact, filled with voices. We heard the eerie chorus, born from the interaction of the solar wind and Earth's magnetic field. We picked up the rhythmic, metronome-like beat of pulsars, those super-dense stellar remnants. We were astonished by the lowest note in the entire universe, the deep hum emitted by the supermassive black hole in the Perseus Cluster, a vibration that resonates for millions of years. And perhaps the most incredible of all, we listened to the gravitational wave chirp, the genuine sound of two black holes merging, a vibration in the very fabric of space-time itself. We even touched upon the very first sound, the roar of the young universe, an echo of which still rings out in the cosmic background radiation. It turns out the silence of space is merely an illusion. In truth, it is saturated with information that our minds have learned to translate into the language of sound, opening up an entirely new level of perceived reality. This cosmic symphony is more than just a collection of fascinating facts. It is a reminder that we live in an incredibly complex, dynamic, and beautiful universe, full of mysteries just waiting to be unveiled. And Heard, thank you so much for spending this time with us. If this journey helped you relax and learn something new, please give this video a thumbs up and subscribe to the channel so you don't miss our upcoming sleep lectures. And don't forget to hit that notification bell. Now, a question for you. Which of the cosmic sounds we discussed today astonished you the most? Or perhaps there's another celestial object whose voice you would love to hear? Please share your thoughts in the comments below. We'd be very interested to read what you think. Good night.